Be here with you guys. That goes without saying.
Yeah, last week was a week for migraines.
Did you have one too?
No, I don't. But my wife, she had a migraine, and it scared her because her symptoms or whatever from having a migraine,
Can't see.
one of her eyes went dark.
Can't see.
What
Yeah.
your sign?
That's why you have to stay home when you get migraine. Because you never know if you re-irritate it, how bad the aura is going to get. You can't get yourself. So that's part of why, like, if I have one.
And my son's girlfriend had a migraine last Thursday.
Oh, right.
Yeah, no, I'm thinking maybe it's the change in the weather, the change in the amount of light, because then you get stressed and then different things trigger. So I only get them about once a year. So I'm hoping that's the one. But no, I always get real suicidal and stuff. I hate migraines. I'm like, I don't want to live like this. Does anybody else in here get them? Do you guys?
Migraines?
Yeah.
I had one last test day. Bad.
Oh,
Really
yeah,
bad.
that reminds me. I had
That's
Yeah, it was, nope, it was weird. I got this weird 24-hour bug.
Yeah.
So the day before test day, I was sitting down to study. I had an exam that day, and at like 10 a.m., within a half an hour, so from 10 to 10:30, I went from being like chipper, right as rain, to just like congested, migraine, just weak. And by the end of the next day, when we took the test, I was fine.
Okay.
But it was just like this 24-hour just sickness.
I think it sounds like you probably have a stress trigger too. Sounds like it. I'm guessing.
No, I was happy. I was
You were
like,
happy
I
with
was
stress?
motivated and like, I've got this.
Sometimes I get stressed and then these muscles get tight, which isn't exactly the same thing as a migraine, but that can sort of bring it on. But I have different things that bring it on too. One time in my life I got a heat stroke, and after that, that's when I started getting these things. So. Anyway, it's all good, but you know what's even better is not having a migraine and being here with you so I can talk about this stuff. So. All right, so where we left off, it feels like so long ago, was the statement of conservation of energy if only a conservative force is acting. So I'm going to remind you that from last time, the last thing that we derived was that the final mechanical energy will always be equal to the initial mechanical energy for any T final T initial. And we called that the conservation of energy. And it holds so long as only conservative forces, in this case only conservative forces, were acting. And we should remind ourselves that E represents mechanical energy of our system, and is kinetic energy plus potential energy, which your author would call T plus U, which is fine. In this case, in this expression, we did this problem where there was just one force acting and it was conservative. So U is just the U from that associated with that one force. The potential energy associated with that one force. But now we should also bear in mind that this expression is even more general than that, because if there is more than one conservative force acting but only conservative forces are doing work, then that U should be considered to be the sum of all the different potential energies that are present for all types of PE present. Let's just say present. Okay. So for instance, this might be the gravitational potential energy plus the potential energy that might be stored in a spring in your system, plus the potential energy that might be stored, in the electric field in your system, plus and so on. As long as all these types of forces are things that are doing the work, gravitational, electric, springs, all those things are conservative. So this would be an expression for our potential energy that we would use in our expression for mechanical energy, such that energy would be conserved for that system. All right, so that's kind of where we left off. And I'm going to pick up from there. So let's talk about what about non-conservative forces? Okay. So if you've got non-conservative forces present, that would be everything that's basically not a conservative force. I know that's kind of seems redundant, but it still, I guess, is worth, one should write defining statements. So all forces are, well, not all forces are conservative, but all forces are either conservative or non-conservative. So those which are not conservative are called non-conservative. And in the case that they're non-conservative, I'm going to use the acronym NC for that. Okay. And in this case, you know, remembering conservative forces were only important in our statement of conservation of energy. They didn't come up for definition before that. And the work kinetic energy theorem was before that, so that's more general. So we can begin with the work kinetic energy theorem. All right, so from the work kinetic energy theorem, we have that the final kinetic energy is equal to the initial kinetic energy plus the work done, the total work done, and that could be the work thought of as the sum of the works by all the forces acting, whether they are conservative or non-conservative. So we can also write this as the kinetic energy plus the sum of all the works from all the conservative forces that are acting. This is as an object goes from its initial to its final position, plus the sum of all the works done by non-conservative forces and moving from the initial to the final location. Okay. And then we will remember that this expression for work done by a conservative force can be expressed in terms of the change in kinetic energy. So I'd have, remembering that the work done by the conservative force is equal to the negative change in potential energy. So I'll make that substitution, negative U final minus U initial, associated with that conservative force. Plus the sum of all the works done by the non-conservative forces. Alrighty, so I've got T final plus U final equals T initial plus U initial plus the sum of all works done by non-conservative forces. And I notice that this is mechanical energy final equals mechanical energy initial plus the sum of all works done just by these non-conservative forces that can't have potential energies associated with them because they don't meet our two conditions, which are that the force depends on location only and that the work done and going from initial to final location is path independent. All right? Okay, so this is our expression for, in the case that we have only conservative forces acting, that's great, we have conservation of energy, but in the case that we have non-conservative forces acting, and we want to use energy considerations, we can use our work energy theorem, which is what this is. All right, so that's our statement of the work energy theorem. All right, so let's do an example with the work energy theorem. This should be very relaxing and remind you of days gone by and introductory physics. So we're going to do example 4.3. In which a block slides from rest down an inclined plane as shown with coefficient of friction mu. Find the speed when it reaches the bottom. with coefficient of friction mu find the speed when it reaches the bottom. And here's the figure. Theta is there. Here's the initial location. Here's the final location. Here's the box sliding along. The box has a mass of m, which can be considered a given, and this length of that surface is d. And that's all we get, except that that coefficient of friction there. And you might say, why is it that I have a coefficient of friction that's a single number? Shouldn't I have a coefficient of static friction, which would be some number between 0 and 1, and then a coefficient of kinetic friction that should be some number that's less than the coefficient of static friction, right? But that assumes, and that is indeed correct, but that assumes that you're talking about two surfaces in which there is dust on the surface, or dirt of some sort on the surface. Because once you get over the coefficient of static friction, you get something moving. Basically what's happening is that those particles are functioning as wheels. And that's why the kinetic friction coefficient, and therefore the kinetic friction force, is lesser in magnitude than the static friction. If two surfaces are clean, you will not have a difference in those two coefficients. So that is obviously also intrinsically the assumption in this statement, since there's only one given. Right? Okay. So, well, I'll give you a couple minutes to do that. That'll be fun. I'll be right back. Remember, you're using energy considerations and not Newton's second. I'm gonna go ahead and start working. All right, so first of all, I've got my situation here. I'm gonna draw a free body diagram. So I've got in my free body diagram, I have, what are the three forces on this object?
Weight.
Yes, yes, normal force, that's right. So weight is mg directed down. Normal force is perpendicular to the surface, and friction force is parallel to the surface in the direction opposing motion. Bad drawing. That doesn't look good at all.
It's fine, you get it.
All right, and I'll make my coordinate system. I have to choose my coordinate system the way that I've always been told to. When an object slides down an inclined plane, in order to use the fact that its acceleration will be confined to movement along the surface, or its movement will be confined to moving along the surface, it won't be allowed to sink in or jump out. I know that all motion will occur along the x direction, and therefore the acceleration, for instance, in the y direction must be 0. All right, so that's why I choose that coordinate system. And I've got three forces acting. All right, so in this case, I want to use energy considerations, the most general of which, E final equals E initial plus the sum of the works done by the non-conservative forces. All right, so I've got two non-conservative forces here, right? You guys agree with that? So gravity is one of those forces that's conservative. You can always write an expression for it in terms of location. Normal force is not a conservative force. It doesn't have a simple function in terms of location that describes it. But the thing about normal force is that whenever an object is sliding along a surface, normal force is always perpendicular to that motion. So it doesn't do work. That doesn't mean it's conservative. It just means it doesn't do work. All right? So it can't have a potential energy associated with it, but it doesn't have to have a term here either. Well, its term here will happen to be 0. All right, so the only non-conservative force here that's going to do non-zero work will be the friction force. So I'll go ahead and start evaluating. So I've got final kinetic energy plus final potential energy is equal to initial kinetic energy plus initial potential energy plus the work done by the friction force plus the work done in theory by the normal force, but in this case it is 0. Okay. So let's go ahead and start seeing what we can do here. I know that initially my object is at rest, so initial kinetic energy is 0. I'm going to choose to let my final potential energy be 0. So that'll be my reference point, will be my final point. All right. Now I'm ready to plug in. I've got my final kinetic energy, 1/2 mv final squared. Sure. All right. And my initial potential energy, it started off up here, so it would be mgh. And in this case, h isn't given, but d and theta are given, so it's the opposite side to the triangle, so it's d sine theta. And then I need plus the work done by the friction force. So in that case, I'll have plus. And the friction force here is constant magnitude, which we'll talk about in just a moment. So I've got friction force times d. It's the simplest case of that integral, times the cosine of 180 degrees. Remembering that what I needed to do to find the work done was integrate f dot dr. Okay? So I've got magnitude of f, magnitude of displacement. Dot product gave me that cosine of the angle between the two. All right. So, and I should remember also that this friction force here is going to be mu times the normal force. And the normal force in this case is somewhat simple in that I don't have too many forces acting, but in theory, one should solve Newton's second law in the direction of the normal force to find the magnitude of the normal force, which is what I will do. So I've got n minus mg, this angle right there is theta, cosine theta, is equal to may, and we already discussed that ay will be 0, so that's equal to 0. And I know we've done this before, but let's just remember that since the x is the direction that's parallel to the incline, and that makes an angle theta with respect to what I'd call true horizontal, then clearly the vertical, as described perpendicular to the incline, must be that same angle with respect to what I would call true vertical. So that's why that interior angle there must be theta. All right. So then I get that the normal force in this case is mg cosine theta, which is kind of an expression we're familiar with, but again, that's just because it's such a simple example. We should, in general, be able to remember that that force comes from an evaluation of Newton's second. Okay, so now I think I'm ready to write this out one more time before I simplify it. 1/f mv final squared is equal to mg d sine theta. Plugging in for my friction force, so I'm going to use notice my cosine 180 degrees is -1, so I'm going to put a minus sign there. Magnitude of my friction force is mu times the magnitude of the normal force, which is mg cosine theta times d. Okay, I'm going to divide both sides by m. And then I've got v final will be equal to 2. I can pull a g out, I can pull a d out, and I'll have sine theta minus mu cosine theta, quantity square root, and that's my expression. Okay, so that's just a reminder of how we do work energy theorem problems. Okay, and we start with our original statement. I should have named it. I'll come back and fix that now. Work energy theorem. That's my starting point. Okay. Are there any questions about that? Great. Let's move on. Force as the gradient of potential energy. All right, so in this case, I just want to be clear. So I will ask you to note that in this case, wherever I think about, whenever I'm mentioning a potential energy, I mean a potential energy associated with a particular conservative force, or a potential energy associated with a particular conservative force, and it would be obviously some sort of function of location. And so your author is not very clear, in my opinion, about noting we are just talking about a particular conservative force, a potential energy associated with a particular conservative force here. When that is the case, the increment of work done by said conservative force is equal to, as always, the negative of the increment of change in the potential energy associated with that conservative force. All right, and we'll recall that both of those are equal to whatever that conservative force was, dotted with dr. Okay. Now, the thing about the potential energy depending on x, y, and z, that means that in order to think about this incremental change in that potential energy, as you move sort of through some incremental change in location, such as dr, that incremental change in that potential energy must be written as, well, it's going to depend on how far you go in the x direction, how far you go in the y direction, how far you go in the z direction, even if it's incremental. So the way to express that is it's your partial derivative of your potential energy with respect to the x variable times your actual change in x, plus your partial change in potential energy with respect to y times your, oopsie, actual incremental change in y, plus your partial of potential energy with respect to z times your incremental change in z. Now, in order to take a partial derivative, the thing that you have to do, like let's say you're taking a partial of this function of x, y, and z with respect to x, then you treat all terms that depend on y and z, you treat y and z during that process, that one partial, as though they are constant values. Okay? All right. Okay, so moving on about from this idea. What I see then from this expression is that, let's say that I want to think about the term here that just depends on change in x. Because what I'm going to have here, if I think about my equality here, I've got 3 terms on the left-hand side, and I've got 3 terms with this dot product on the right-hand side. So if I think about just the x term from the left-hand side, I've got minus du dx times change in x is equal to the x component of the conservative force times dx. In theory, I could have written this out as all 3 terms, and that is all 3 terms. That might have been nicer mathematically. Why don't I do that? Okay. Let's put a pin in that. So in this case, this is the expression for my incremental change, the negative of my incremental change in my potential energy associated with my force, my conservative force. And here I have the work done by my conservative force during that time that I went through that incremental change in location dr, where dr was dx in the x hat plus dy in the y hat plus dz in the z hat. Now, the only way that these two sides can be generally equal for any infinitesimal change in location dr is if each of these terms are independently equal. That way they'll hold for if you change dx and change dy and change dz. All right, so from this equality, it must be that, and I'm going to write it this way, fx must be equal to minus du dx, where those are partials. Fy must be equal to the negative partial of u with respect to y, and fz must be equal to minus the partial of u with respect to z. And I'm going to go ahead and put a box around that because that's the result that I wanted. So that if you know the potential energy associated with some conservative force, then you can find the form of that conservative force. All right? It's obviously a vector quantity. It has x, y, and z components, and you can get them by taking these partials. Okay. Another way to write these relationships would be to note, okay, I guess I can do this. To note that I can summarize this as f is equal to minus x hat partial with respect to x acting on u plus y hat partial with respect to y acting on u plus z hat partial with respect to z acting on u. And in that we see, oh, that's it. That we could state that very elegantly if we just chose to use the del operator. So this is equal to minus the del operator acting on the scalar function u. And when we act with the del operator on a scalar function. I've already introduced this, but let's remind ourselves that we're taking something called the gradient in that case. So I'm getting an expression for that conservative force in terms of the potential energy associated with that conservative force. All right. And remembering that this conservative forces, conservative potential energies must depend just on sort of location and be functions. All right. So just because I just want to remind you that this thing here is the del operator. If you don't remember, look back in your notes from the beginning of the chapter. We defined it. And this operation here is called the gradient since it is acting on a scalar function. All right. So any conservative force can be derived from its expression for potential energy. That's all you need to know. I guess I'll write it. Okay. All right. So let's go ahead and be clear again that, you know, there won't be, just as in the example we just did, there are some forces that won't be changing mechanical energy, but they also aren't conservative. And examples of those would be things like normal force. Magnetic force, magnetostatic force is another one, because it can only change direction of a particle, it can't change its energy. But again, those things won't have potential energies associated with them because they can never do work. All right. So just because they never do work doesn't mean that they'll have potential energies associated with them. All right. What else do I need to say here? There's another, this is a very, very useful expression, obviously, because you can always get your force from your potential energy. There is another useful expression. Which is that you can always find the infinitesimal change in potential energy associated with some conservative force from that force, which I think that we all remember is minus Fc dot dr from the definition. But that is also equal to, in this case, minus Fc, I got two minus signs, so del U dot dr. And the reason I'm writing this is it's really, I'm more interested in the mathematical thing, which is that the incremental change in this value of potential energy is equal to the gradient of potential energy dotted with dr. Okay? So we derive that sort of numerically. And if you want to maximize your infinitesimal change in potential energy for some fixed amount of infinitesimal change in location dr, you would have to do that by moving a direction that's parallel to del u. You guys agree with that? So that'd be the direction associated with the gradient is the direction of the maximum change in u value as you go in that direction. All right? Okay. That'll be something that you get to derive in your homework. I should talk about homework. This homework's not going to get a due date until I turn back your previous homework that I'm holding on to. But if you want to know what the next homework assignment is, I can tell it to you right now, but it's not officially assigned at this time. But why not? It doesn't hurt you to have more time, right? Is that true? Or will you guys be stressed if I give it to you? Do you want it or do you not want it? Want it? Want it? All right, let me just see over here. Week by week. This is homework number 6. And it will be chapter 4. We'll do problems 2, 7, 18, and 23. And after today, you will have everything that you need to do. And I don't know when it's due yet. It'll be due a week from whenever I return this other homework, which hopefully will be Wednesday. Okay. Make sure that showed up. Is that not? So that was homework, that's homework 5. Sorry, let's edit that. Okay. All right, so yeah, one of these problems you'll be sort of, I think it's actually, I can't remember, maybe number 7. You'll be talking about some of the things that are associated with the direction of this gradient. Okay. All right. So, that's all I wanted to say about that. Let's move on to the next topic. The second condition for the force to be conservative. We had 2 conditions for a force to be conservative. The first was that the force depends on location only, and the second one was that the force, the work done by the force cannot be path dependent. Going from point 1 to point 2, it could not depend on which path you take. So we're going to talk a little bit more about that second condition. All right, so what we need is we need that the path integral from point 1 to point 2 of f dot dr does not depend on the path. So it's equal to the same number for all paths. And I think that your author is pretty wise to not derive this for you, but you could do, but I'm going to take his lead and say, let's try not deriving this and see how it goes. And I'll just say that is true if and only if the curl of the force is equal to 0. All right, so we need to talk a little bit about what that thing is, that curl. And I guess we kind of already, this is really the whole point of that section, and that's all I'm going to do with it, except to do an example with it. Right. So let's do an example using this piece of information. I'm going to do a slightly different example than your book does. I'm going to do, because I just did it before I even saw that your book did one. So the question that I'm going to ask in my example is the gravitational force conservative? All right. So what I'm going to think about is I'm going to think about having some mass, which is a source of a gravitational field, and I'm going to let it be, in this case, spherical. That doesn't have to be, but it does. Its center of mass would have to be chosen as my origin for this. You know, I'm going to allow the origin to be at the center of mass of my source of gravitational field, and I'm going to say that my source gravitational field has a mass capital M. All right. And then I've got some point. Maybe it's over here that I want to think about. Don't draw it there if you don't want to, but I'm not going to draw it there. But I want to think about the gravitational force on that point. So what I'm going to do, and it doesn't matter, so without lack of generality, I can sort of define that this axis, this z-axis is going to be the line that goes from the center of my object through that point and on. So that without lack of generality, I can draw this arbitrary point at an arbitrary distance from my sphere to be on the z-axis as a choice of coordinates. And I'll call that point P. And at that point P, I'm going to place another mass M. Okay. And so in this case, which is the most general possible case, I note that the gravitational force That's the most general case where I just have two objects interacting, which is all that I want. The gravitational force can be written as negative GMM over z squared z hat. All right. So I would like to know, for one, is the gravitational force conservative? Well, it can be written as a function of location. I just did it. The only other thing that it needs is that it's work done by would not depend on the path taken, and I find that that will hold in the case that the curl of the force is 0. So I'm going to check the second condition for it to be conservative using this curl relationship. All right, so del cross FG. So remember that the curl is equal to the determinant of the 3 by 3, whose first row is unit vectors of the rectangular coordinate system. Second row is partials with respect to x, with respect to y, with respect to z. And third row is x, y, and z component of the vector function. Okay, so in this case, I've got x hat times, and we can go ahead and notice that in this particular case, the way that I've written it, the x component is 0, the y component is 0, the z component has this dependence on z, minus gmm over z squared. Okay, so my x component is partial with respect to y of this object here that's in front of the z hat, which is obviously has no dependence on y, so that's 0. Minus partial with respect to z of 0. Okay, so that's just going to give me a 0. Minus y hat, partial with respect to x of this object. Again, it's going to give me 0. Minus partial with respect to z of 0. So that's 0. Plus z hat, obviously times 0. Okay, so yes. The gravitational force is conservative. Check. Okay. Now, I'm going to add a second part to the question, which is, what is the form of the potential energy associated with that force? All right. Oh, I only have 2 minutes. Okay. Well, I'm going to give you just a second to work on it so that I can work it out, and then I'll present that in a moment. So we'll go ahead and evaluate this. So I've got, okay, I'm just by that time. All right, so what have I got here? I have to think about minus the integral from R naught to R of f sub g dot dr minus the integral from R naught to R of minus g m over R squared R hat. And yeah, I'm still thinking about this point here, but I'll notice that the z hat is also the R hat in that case. Yep. Still thinking of the point up here, but I'll notice that the z hat is equal to the R hat in that case, just using my expression. And then dotted with dr, which is dr R hat. Also, and I have the integral, oh, I'm over. In this case, where I want my potential energy to be 0 will be the value of infinity, and this should just be R. And I've got G, M, M, R to the minus 2 dr, which gives me G, M, M, R to the minus 1 over negative 1, which I have to evaluate from infinity to R, which gives me negative G, M, M over R minus 0. And this is my expression for the gravitational potential energy as a function of location. The last thing I'm going to want to do is find the expression for the gravitational force from this and make sure that it agrees with with what is known. So we'll do that last part where we'll find FG and check that it agrees with what we know. All right? So we'll find FG from you next time and do some more cool stuff. All right. See you Wednesday.
I want to get started on my stuff. But that's the main thing. I think the other two will be simple compared to the. Yeah. But I'm assuming it's the same sort of thing, but now you have cosine theta. Yeah, and then
I got 2 points.
right. E